Hi everybody, Physics Ninja here. Today we're going to apply Coulomb's law in order to look at two problems. Okay, the first problem is I have 3-point charge and they're all on the x-axis. And my goal here is going to try to find the force on the charge labeled Q3. Q1 is a positive charge, Q2 is a negative charge, and Q3 is also a negative charge. So how would you find the net force acting on Q3 using Coulomb's law? And the second problem, it's kind of the same charges. I have them in a different configuration. So I have them in kind of the XY plane in 2 dimensions. So how would this change the problem? How would you apply Coulomb's law to find the force on Q3, for example? So let's go ahead and set these problems up. I'll show you how to solve them. If you have any questions, leave them in the comments section below. Again, remember, like the video if you thought I did a good job, and also consider subscribing to my channel. All right, let's get started. All right, so here's my first problem. My goal is to find what is the net force acting on this charge Q3. So let me go ahead and kind of just draw it over here. Here's Q3 right here. And Q3 is negative, so I can go ahead and maybe just remind myself that's a negative charge here. All right, so let's go ahead and get started. So Coulomb's law, you might see it written like this, KQAQB divided by R squared. R squared, or R rather, is the distance between the two charges, A and B. Sometimes it's written with a different constant in the front instead of this value K. It's sometimes written as 1 over 4 pi epsilon 0. And that's okay. If that's what's done in your textbook, the only thing to realize is that that value K is actually equal to 1 over 4 pi epsilon 0. And if you substitute the numbers, you look this up in your textbook, you look this, substitute everything in your calculator, you should get 9 times 10 to the 9, and the units for that are going to be newtons meters squared per coulomb squared. And you need those units in order to have newtons for the force at the end of the day. All right, so how do you find the force? Well, let's first look at them in pairs. Coulomb's law works with 2 charges at a time. So what we have to do is, if we're looking for the total force on Q3, well, there's going to be an interaction between Q3 and Q1. So let's go ahead and draw. What is the direction of that force between Q1 and Q3? Q1 is a positive charge and Q3 is a negative charge, which means they are attracted to each other. So if I go ahead and draw the force, that means Q3 wants to get closer to Q1. There is an attractive force there. So we're going to go ahead and we're going to call this force F1. So the direction has to be to the left because it's attracted to Q1. All right, what else do we have? We also have an interaction here between the charge Q2, which is negative, and the charge Q3, which is also negative. So if I'm looking at all the forces acting on Q3, that means it's also trying to be being repelled by Q2. So that means over here I should probably have another force, and I'm going to label this one F2. So this is interaction of Q2 and Q3. All right, let's remind ourselves that this here is the charge Q3. So now the only thing that's left is we have to find how big those 2 forces are. So let's go ahead and do that. So the force F1, in order to find its magnitude, well, all you have to do now is use Coulomb's law. So F1 is going to be equal to, let's use this first equation over here. K is our constant, 9 times 10 to the 9. Our first charge here, we're going to call it Q1. Our second charge now is going to be the charge Q3, the one we're interested in. And now it's divided by R squared. And R squared is the distance between both of those charges. If I look on the figure here, it would be the distance between this guy and Q3. So let's go ahead and call this distance here D1. Okay, so I have to add this to Coulomb's law, D1 squared. All right, so all you have to do now is substitute in all the values. So for K, we get 9 times 10 to the 9. I'm not going to write the units. Q1 is listed over here as 5 microcoulomb. That's 5 times 10 to the negative 6 if I want to convert it into coulombs. Q3, now Q3 is negative 2. All right, microcoulomb. I'm actually just going to write it as 2 microcoulomb. I'm going to drop the negative sign because the negative sign here is only going to tell me something about the direction of the force. But we know the direction of the force because one charge is positive and the other one is negative. So there is no real reason to put negative signs here if you're looking at interaction between point charges. We automatically know the direction of the force just by looking at, are they both positive? Is one positive and the other one's negative? All right, and now we also have to divide by the distance squared. Now in this case, this is the distance between Q1 and Q3. If I look down at the figure, I've given you some distances here. You should see that this distance should be 0.6. So 0.6 meters, and I have to square that value. All right, now be a little bit careful when you enter this in the calculator. I did this, and hopefully I did it correctly. At the end, I get 0.25 newtons. Now, if you kept the negative sign here, you would get a negative 0.25 newtons, but negative simply tells me that the force is attractive. Okay, so that means that this force here is 0.25 newtons, and it's pointing to the left. All right, now we have to find the magnitude of this other force. So let's go ahead and we're going to apply Coulomb's law yet again. So again, now in this case, it's K. The two charges interacting now are Q2 and Q3. Q2, Q3, and now it's going to be divided by a different distance, right? The distance is much smaller, so we're going to call this D2. So D2, and I have to square that value. All right, let's go ahead and substitute in all the values. So we get 9 times 10 to the 9 for our K constant. Q2 has a magnitude of -3. Again, I'm not too worried about the magnitude. That tells me the direction of the force. 10 to the -6 because we're dealing with microcoulombs. Q3 is still the same, 2 times 10 to the -6. And now I have to divide by this distance. This distance is 0.2, and I have to square that value. All right, you place everything in your calculator again. In this case here, I got a stronger force. I got 1.35 newtons as the magnitude of F2. Let's go ahead and write this on the figure. So we get 1.35 here, and I get a vector that is 0.25 newtons pointing to the left for the red one. And that's it. All you have to do now is find what is the net force. You can tell just by looking at this that the net force is going to have to point to the right-hand side. All right, again, my goal was to find F net. The definition of F net as a vector means you have to add up all of the forces acting on the charge. In this case, I have 2 of them. Okay, so what I'm going to do now is I'm going to assume that everything pointing to the right-hand side is going to be a positive force, and everything pointing to the left-hand side is going to be a negative force. So at the end, if you want to add both of these up, I would say there is a positive 1.35 Newton force acting to the right, and there is a negative 0.25 Newton force acting to the left. So my net force at the end of the day, simply have to evaluate both of those. My net force at the end should be 1.1 newtons. In the direction, since it's a positive value, the direction of the force has to be like this. This is the direction of F net. It's in the same direction as the force F2. Okay, so there's a nice simple application of Coulomb's law when there's more than 2 charges. Let's go ahead and look at problem number 2 now. Okay, so here's problem number 2. Again, we're going to look at the net force acting on charge Q3, except now it's kind of like a 2-dimensional problem. So let's first start again by labeling all the forces acting on Q3. So there's an interaction between Q1 and Q3. Since Q1 is positive and Q3 is negative, there is an attractive force on Q3, and that force should be in this direction over here. We're going to call this force F1 again. All right, and that's the direction. What else? We also have an interaction between Q2 and Q3. If I'm looking at all the forces acting on Q3, that means I need to add another vector. I need to add this vector over here. We're going to call this F2 again. Again, these may not be the same. We're going to evaluate how big those vectors are, but for now, let's just label them like this. So the first thing we're going to do is we're going to apply Coulomb's law. Let's calculate how big is F1. What's the magnitude of this vector? Okay, so in order to do this, so let's write down our equation. So we have F1. Again, it's the constant K. That's the same. Q1. Q3 and divided by, again, it's the distance squared. Well, what's the distance in this case? If I go back to the figure, it's going to be the distance between this guy and this guy. This is the distance D1 in this case. It's different, right? It's not the same as what we previously had. So this is d1 squared. So actually what you need to do now is you need to do a little bit of math in order to find what is d1. Well, this we can use just Pythagorean theorem, right? We know that one side is 0.4, the other is 0.2. So that means that d1 is simply going to be root of 0.4 squared plus 0.2 squared. All right, you put those numbers in the calculator, you should get it's approximately 0.45 meters. All right, now you can go ahead and substitute everything to find how big this force is. So we get 9 times 10 to the 9. Q1 was 5 times 10 to the negative 6. What else? Q3 is still negative 2 microcoulombs. I'm not going to put the negative sign again. That only tells me the direction of the force. And at the end now, I need to divide by 0.45 and square that value. Okay, you substitute in all the numbers here. What you should find now is a force that's approximately equal to 0.44 newtons. And this is the direction here. It's kind of at an angle. All right, our other goal is to find what is F2. Well, F2 should be pretty much identical to the previous case that we found, right? Because we haven't changed anything. So let's just write it down just for completeness. We get K. We get Q2, we get Q3, and our distance now, this is our distance, D2. It's the distance between both of those charges. So we should get let's just call it D2 over here. D2, and we have to square that value. All right, you could tell that the magnitude of this force is going to be the exact same, which we had 1.35 newtons. All right, let me go ahead and write this in the top figure. So we have both of our forces. Our goal now is really to find what is the net force. So what you have to do now is you have to add these up as vector quantities. So what we're going to do in order to do that, we're going to do a little bit of math. So we're going to have to break the force F1 down into two components. Let's start off by making a little bit of extra space. We already have all our magnitudes here, so I can get rid of this information. What else? I already have my magnitude on my vector diagram over there. Okay, now let's go back to this figure. What I'm going to do now is I'm simply going to move this to give me a little bit of extra space, but this is at F1. I'll just move it over here. All right, now let's look at our diagram. This is what I'm going to do here. I have a line, which is the x-axis here. I'm going to go ahead and I'm going to kind of draw a parallel line to that one. Now on the inside over here, if I call this angle here theta, what I want to do is I should notice that this here should also be the same angle theta. Okay? And my goal now is simply to break the force down into components. So F1 is a vector along this angle. What I'm going to do is I'm going to break it down into two components. This here is going to be the x component of F1, and the y component of F1 is going to be pointing down like this. So this is going to be the y component of that force. Now if you do a little bit of trigonometry, you should realize that F1, x, should be equal to the magnitude of F1 multiplied by cos of that angle. And F1y should be equal to F1 sine of the angle theta. So it would be nice if we know what that angle theta is, but we can actually determine the angle theta by looking at our first diagram, right? The angle theta you could find right here. And I can use any of the trigonometric functions in order to find this. I'm going to use tangent, okay? If you write down tangent of theta, you should say that's opposite over adjacent, right? 0.2 over 0.4, which is just equal to 1/2. So at the end, if you take the inverse function, tan negative 1 of 1/2, you should get an angle equal to approximately 26.6 degrees. All right, now I'm in good shape. I can go back and actually find what the magnitude of both of those forces are. So for this guy here, I substitute 0.44 for F1, and then I do cos of 26.6. For the next one, it's 0.44 multiplied by sine of 26.6. All right, so we have two magnitudes now. We're going to have F1x and F1y. We know the direction by looking at our diagram. F1x, I substituted things. I got approximately 0.39 newtons, and F1y was approximately 0.2 newtons. Okay, so I got to use these two values now. And in order to find the net force, you have to find the net force in each direction. So let's go ahead and do that now. To find the net force, all you have to do now is find the net force, or the component of each one. Okay, so let's go ahead and write down our equations for the net force in each direction. Again, this simply means I add up all of the forces, and I only add up their x components. In this case, there's only one, and what I'm going to do to add them up, I'm going to choose just a standard XY coordinate system, so everything pointing to the right is positive. Everything pointing up will also be positive. There's only one force in the x direction here. It's this one component, and I'm going to set it as negative because it's pointing to the left. So 0.39. Again, positives or negatives are only telling you something about the direction. All right, so we have that one. How about the forces in the vertical direction? We have to add up all the forces in the vertical direction. There's two, right? I have F2, and that one's pointing up, so I'm going to call that positive. And there's only one component acting down. It's only this component of F1, which we calculated here is 0.2. So notice these have two different signs because they're in different directions. So at the end, the net force in the vertical direction is simply going to be 1.15. All right, perfect. Now, the last step now is we have it in components. We may want to calculate how big is the net force and what does it look like on a diagram. So we have a component of this net force. Let's just make it in black over here. We have a component of the net force, which is in the x direction. And we also have a component which is in the vertical direction. So at the end, if you add up both of those, I should have a vector that kind of looks like this. This is really the net force direction. First thing I could do is I can calculate what is the magnitude of this net force. Since you know everything about the vector, you know both of its components, you simply use Pythagorean theorem in order to solve this. 3/9 squared plus 1.15 squared. Again, I don't have the negative sign because at the end I just end up squaring it. Whether you write it in there or not, it doesn't bother me. 1.2 newtons is the magnitude of this net force. The other thing you may want to do also is say define what is the angle. And I say I define this angle here, alpha, something like this. Again, if you know both components, you know the x component of that force, F net x, and F net y, we should be able to use our trigonometry in order to write down an expression for what is this angle alpha. So let me go ahead and do that over here. Here, let's make some space. So what I'm going to use is tangent again. I kind of like to use tangent. So you should be able to write that tangent of this angle, alpha. Tangent is going to be the opposite over the adjacent. So it's F net y over F net x. So we substitute in our numbers, and at the end you want to take the inverse. So alpha is tan of -1. F net y was 1.15. And F net x, we had 0.39, the magnitude. Okay. You should get an angle alpha that's approximately equal to 71.2 degrees. Okay, so you can go ahead and draw that one here in this figure, 71.2 degrees. Now, depending on how you defined it, you could have defined this angle. At the end, that doesn't really matter. As long as you have a vector where you have a magnitude and you have some direction, or you could also just write it down into components. We have an x and a y component. We've defined the total force acting on charge Q3. All right, thanks for watching, folks. Hopefully you understood this problem.